Our commander can be used to fit linear models to datasets, and we're going to illustrate undertaking a linear regression analysis with one of the datasets that's available in the Modern Applied Statistics with S package. So the first thing we're going to do is to load the package from the Tools menu, and when we've located the package after searching through the long list, we click OK and note that it's been loaded. So now we can go and import this data through the data menu, reading data from one of the attached package, double click on mass and then locate the data set called Whiteside. So this is a set of data on the effect of insulation on gas consumption in a house. So there are only 3 columns of data in this simple data set. That's a dichotomous variable insul, which indicates whether the measurement was taken before or after insulation was installed, temp, which is the temperature, and lastly gas, which is the gas consumption for the week measured in thousands of cubic feet. So we can take a quick look at the data with the View Datasets button, and we see the 3 columns as described here. So 1 categorical variable and 2 continuous variables. So here the gas is the response variable, the y variable, and temperature is our explanatory variable or x variable. So one thing that we might want to do is to plot this data, so we can make use of the graphs menu, and if we look for scatter plot, we'll then get this dialog box. So our x variable, as I mentioned, is temperature, y variable is gas, and if we leave in the least squares line and do plot by groups, and we use the variable insul, which is our binary variable, and then click OK, we'll get a graph out like this. So we see that the different parts of the data corresponding to measurements before and after installation was installed are shown with different colors and symbols, and also that on this plot we've got a fitted linear least squares line fitted to each of the subsets separately. So then if we wanted to actually fit these models ourselves, look at what the coefficients are to test whether these slopes are significantly different to 0, or to consider whether we could use a single model to describe both of the datasets, or whether we need this more sophisticated model we've got here, where we've got separate intercepts for each dataset as well as separate slopes. So if we go to the Models menu, so Statistics menu and Fit Models, as we don't have a model fit at the moment, and go to Linear Regression, this allows us to perform a simple linear regression model. So let's say we want to do this for the before data. So if we call our model just before, and our response is gas, explanatory variable is temp, but now we want to subset based on the last variable. So we write in the R command that we would make use of to fit this model. So the column insul, and we're testing for the condition where that particular variable is equal to before. Click OK, and we'll notice that it's fitted this model and given us the intercept and slope based on temperature. So as the temperature increases, we're changing the gas consumption by this amount. This is prior to fitting insulation. So we could also then go fit models and then do linear regression again. This time if we call the model after, so response again gas and temp, and we just go through the same approach here. But now we have insul equals after. So we say that we fitted these 2 separate models before and after, and we can see that there seems to be a difference between the intercepts. So that would be the hypothetical situation where the temperature, or rather it's not hypothetical in this case, when the temperature is 0, then the gas consumption will be, beforehand it was 6.85 thousand cubic feet units, and afterwards it would be 4.72 thousand units. Now the slope is different for after insulation, but although it's smaller, we already starting off at a lower value, which is what we saw in our graph here. They're only starting to converge when we get to higher temperatures, and that's probably because there isn't actually a need for heating as much at those temperatures. So what we could do is we could then look at the diagnostics for, say, one of these models. So through the models menu, graphs, basic diagnostics plots, and then we bring up the graph here and we get 4 particular diagnostics that may be of interest. So the residual versus fitted plot, so these are the fitted values for the model for the data after insulation plotted against the residuals, which are the differences between our observed gas consumption and what the model's telling us it should be. And there's a normal probability plot which is testing some of the other assumptions behind the linear model. And apart from a few data points, that assumption seems to be reasonable for this data. So let's say we wanted to consider fitting a more complicated model. In that case, we'll go, rather than linear regression, we'll go to linear model, which is more general. So if we just call this gas 1, and our response variable is gas, and it's very helpfully remembered various things here, and temperature, but if we assume that we have a fixed difference between the two, so this corresponds to different intercepts but a common slope, so the change with temperature is the same before and after insulation, but we believe that we will start at a different amount of consumption at 0 degrees. So if we run and fit that model, we'll notice here that when we're testing these particular coefficients, they're coming out as significant, which is suggesting we need them in the model. Now we could also consider having different slopes to see whether that's important or not. So we go back to fitting the models in the linear model, and now we would add an interaction between those two variables. So if we save this as gas 2, notice now here this interaction term means that the baseline group, which is the before data, will have this particular slope, which if we scroll back to our previous model, we can see that for the before data it's the same slope. And then if we're looking at the after data, we have 0.11, which is getting the value we had when we fitted the model separately. And similarly, if we consider the intercepts, then we can see that that's the case. So what we might want to do is, let's say we want to compare two models. So this particular model, to do an F-test to say whether simplifying the model leads to a significantly worse fit. So we select our models, gas 1 and gas 2, which we saved, and it runs the ANOVA function, and we're getting a very significant test, a very small p-value, indicating that we can't simplify the model in that way.